subtopic 1.3 Factors Affecting Reaction Rate. In this subtopic, I am going to explain the factors that affect the rate of reaction, illustrate the effect of temperature by using Maxwell-Boltzmann distribution curve, and what is Arrhenius equation. Lastly, the relationship between temperature and activation energy to the rate constant based on the Arrhenius equation. There are a number of different things that we can change to make a chemical reaction faster. Here, I will explain the concept of collision theory and how it can be used to explain the effects of 4 different factors on the rate of a chemical reaction. First, effect of concentration. Increasing the concentration of reactants in solution increase the rate of reactions as there are a greater number of particles available to react. Thus, the rate of the reaction is directly proportional to the concentration of the reactants. This video shows how the different concentration affect the rate of reaction. When molarity of reactants in solution increases, the number of moles per unit volume increase. This will increase the frequency of collisions between particles. So, effective collisions increase and therefore the rate of reaction increase. Effect of pressure. Increasing the pressure of a reaction involving gases forces the gas particles closer together. This will increase the frequency of particle collisions and therefore increase the rate of reaction. Effect of temperature. Increasing the temperature increases the kinetic energy of particles. From this video, we can see the rate of reaction increase as temperature is increased. So, at high temperature, the average kinetic energy of molecules also increase. The number of molecules achieve enough energy increase, therefore frequency of effective collisions increase. The effect of temperature on reaction rate shows by Maxwell-Boltzmann distribution curve. The total area under the entire curve is the total number of molecules in the gas. If we heat the gas to a higher temperature, the peak of the graph will shift to the right. As the graph shifts to the right, the height of the graph has to decrease in order to maintain the same total area under the curve. Increasing the temperature increase the average kinetic energy of the particles. The area under the blue line shows number of particles with energy greater than activation energy at T1. The area under the red line is the number of particles with energy greater than activation energy at T2. Only the particles with enough energy, meaning molecules with equal or higher energy than EA can react. At T2, a greater proportion of particles have energy greater than the activation energy. Therefore, the rate of reaction increases. Size of the reacting particles also affect the rate of reaction. Increasing the surface area of solid reactants increases the number of particles that are exposed and available to react, and as a consequence, this increases the frequency of particle collisions. Therefore, the rate of reaction increases.
This illustration shows how the total surface area of a cube can be increased if the cube is diced into eighths. An analogy to this would be a log of wood being split into many, many smaller pieces.
A catalyst speeds up a chemical reaction without consuming it. A catalyst provides an alternative route for the reaction with a lower activation energy. This means that particle collisions need less energy in order for a reaction to occur, increasing the rate of the reaction.
Conditions, hydrogen peroxide decomposes into water and oxygen at an extremely low rate. But a catalyst, manganese 4 oxide, can be added to rapidly increase the decomposition of hydrogen peroxide. Here we see gaseous oxygen being evolved rapidly and an enormous amount of heat being released from the reaction.
The rate of chemical reaction are strongly affected by temperature. The Arrhenius equation gives the following relation between rate constant and temperature. The equation can be expressed as K is equal to A times E raised to negative EA per RT, where K is a chemical reaction rate, or called as rate constant. A is frequency factor that is determined experimentally as it varies with different reactions. EA is the activation energy, which is the energy that the reactants must acquire before reaching the transition state. R is the gas constant and its value is 8.314 joule per mole Kelvin. T is the absolute temperature in which the reaction takes place in unit of Kelvin. And lastly, E. This is a mathematical constant, where the expression of E raised to negative EA divided by RT is the fraction of the molecules present in a gas which have energies equal to or in excess of activation energy at a particular temperature. The Arrhenius equation can show the effect of a change of temperature on the rate constant and therefore on the rate of the reaction. If the rate constant doubles, also will the rate of the reaction. The higher the temperature, the faster chemical reaction will proceed. Quantitatively, this relationship between the rate of reaction proceeds and its temperature is determined by the Arrhenius equation. Let's say if we increase the temperature by 10 degrees Celsius from 20 degrees Celsius to 30 degrees Celsius. At higher temperature, the probability that two molecules will collide is higher. This higher collision rate results in a higher kinetic energy which has an effect on the activation energy of the reaction. The frequency factor A in the equation, also called the pre-exponential factor, is referring to frequency of correctly oriented collision between the reactants which lead to products. The activation energy is the amount of energy required to ensure that a reaction happens. This expression counts the fraction of molecules with energies equal to or in excess of the activation energy can be obtained from Maxwell-Boltzmann distribution. Assume an activation energy of 50 kJ per mole. The value of gas constant given. For calculation, we must write as 50,000 joule per mole in order to get parallel with unit R. To count the fraction, we apply this expression formula. The amount of fraction at higher temperature is almost double compared to lower temperature. We can see that the fraction of the molecules able to react has almost doubled by increasing the temperature by 10 degrees Celsius. This causes the rate of reaction to almost double. So, for the conclusion of the Arrhenius equation, rate constant is directly proportional to temperature. When temperature increases, the fraction increases. Therefore, rate constant also increases. According to rate law, rate of the reaction is directly proportional to the rate constant. The reaction at higher temperature has higher value of rate constant. Therefore, the rate of reaction also increases at high temperature. A catalyst provides an alternative pathway for the reaction by lowering the activation energy. At the same temperature, without catalyst, the fraction is lower with higher activation energy. With catalyst, the fraction is higher with lower activation energy. We can see that there has been a massive increase in the fraction of the molecules which are able to react in the presence of the catalyst than without catalyst. From the Arrhenius equation, rate constant is inversely proportional to activation energy. When activation energy decreases, the fraction increases, therefore the rate constant increases. So, from the rate law, rate of reaction is directly proportional to the rate constant. A reaction with the presence of catalyst has higher value of the rate constant. Therefore, the rate of reaction also increases. In fact, the catalyst speed up the reaction.